All right, so what I'm going to demo world, hello world demo / discuss is some of the work I've been doing lately with the kind of rover architecture software stack that I've been working on. I've talked before about this Yak API kind of web server that can provide sort of a consistent interface for communicating with the rover or communicating between rovers. And so I've just been kind of playing with that over time and iterating on it. One of the challenges was how to decouple the implementation of how a specific rover operates, like what features it has and how you interact with the low-level hardware and all that. How do you decouple that from kind of this interface to be able to provide the sort of abstraction that would allow a more heterogeneous set of rovers to be able to operate as if they were very similar? That's the idea I've been exploring. Previously, I had like the very first demo, I believe I had it set up to where if you asked the rover to do a command, for instance, it would end up running a Python script that I had written that would directly interact with like the Raspberry Pi pins to cause the motors to go, for example. And then what that and where the layer was, it was really about like motor control. So I would say like, oh, this Python script is what you use to control a motor. And you would say as the argument, like, this is the motor I want you to do, and I want you to run it at the speed. That works great for my rovers because they all have 2 motors and that's about it. But it doesn't necessarily work for everything, and I wasn't super happy with it. Also, the language that you use to interact, I've just been kind of sticking with the same kind of text-based command language, where if you want the rover to go forward, you say forward 100 or whatever. So super simple, right? I think we've had many discussions about kind of more advanced ways to think about it, but for now, that's what I've been working on. And so that was another thing where I wasn't super happy with the way the abstraction was, because the command processing was built into the API itself. So if anyone was going to use this Yak API server, they had to like be able to understand that they were going to understand this language and they'd be stuck with it. And so what I've changed since then was that now instead of having a motor controller adapter, so where you would say like, this is the script that you call to move the motor, now there's an adapter that says, here's the script that when you receive commands, send the commands to that script and it's going to figure out what to do with it, which means the API doesn't really care so much what those commands look like. They can be any sort of language that you wanted. Here's kind of the result of what that looks like if you were to set up a cat as the Unix command cat, just echoes whatever is sent to it. So if you set up cat as your CI command, then if you send any command to it, you just get that as the result back. And so you can imagine replacing that with a Python script that does something else. So that's sort of where I had left it off previously. The stack that I was envisioning in my mind was very distinct from ROS, for instance. Like, we've had conversations about ROS, can't get away from it. But I think it was still kind of hard to map to my own brain. Like, why would I want this giant mess of dependencies to do what exactly? What is it doing for me? So I think through this exploration, I've almost found myself reinventing ROS. And so maybe now I understand it better. And that's what I'm going to kind of talk about here today. My original intention was to use, I think I used the phrase like, Unix is my robot operating system. Everything was going to be really just tied to, look, I've got this Linux system. Now we can have a Raspberry Pi. We have a full featured operating system. We don't need like these other things. And that's certainly, my own background, certainly much more comfortable with all those sort of primitives. I found a few awkward, slightly more difficult to deal with challenges that brought up as I went to use it. And I was just like, this is just kind of not as convenient as I might like. And so that's the that's the slippery slope towards reinventing ROS, I think. So that's what I'm starting to figure out. But so what I've done, instead of using ROS, because I was like, I just don't understand it, I'm going to reinvent it from scratch. What I did was I've re-implemented everything around Redis. So Redis is a kind of it's a server that acts. I'll open another tab because I already have it. It's a server that's essentially a data structure service. So you start this thing on a computer and it exposes essentially data structures over a protocol that you can interact with. So folks use that for as a data store for simple key value pairs. So if you're in a web application that had like, you didn't want to have a SQL database, you just wanted to say, look, I'm going to set a key and the key will be name, and also the key name to be Rhett, for instance. And so it's got like key value stores, it's got lists, it's got sets, and the simple protocol to interact with it. And so I was kind of, and I'm very familiar with that from kind of more of a web background. So I thought that might be a good primitive as opposed to directly using Unix stuff. And so just to give you an idea of like, compared to ROS, for instance, getting started with Redis, I think is very easy. So I just created a compose file and it just uses the image Redis. And then Redis is so well known that it's just like a Docker default. You can just install it anywhere and it just runs. I run the Redis CLI. As I mentioned, there's simple data structures, so I can set a value. I will set it to Rover. And then I can get this key value. I can create a set of things. So I can push to yak list, the prime, no, the L push, batteries. What was my other one? Stubborn. And then you can pop things off of that. So it's got quite a few features that are kind of helpful for if you want to store data persistently or semi-persistently, independent of like a Python script. So if you run a Python script, you sort of want it to, the easiest thing to do is to say, have it run, have it exit, and then make a change, you run it and exit again, and make a change, run it, exit again. Instead of trying to store data in memory, you want it to go somewhere else. So you can choose a SQL database, you could choose a file on disk, you could choose, in this case, Redis. And because it has some of these data structures that I thought might be helpful. So what I ended up doing, and again, this is running on Yak Prime, the VM that I set up that was sort of going to act as a fake rover, a simulation of a rover. I don't have any of the hardware that might be needed to do sort of the Unity-based or NVIDIA-based full-on simulation. So I was like, how can I simulate a rover at this level of granularity? So I started writing a simulation from scratch. And just with the focus of trying to really prove out the architecture more than needing to have a realistic simulation. And so, and it's kind of fun to think about how a simulation works in a this is in a 2D environment. So my simulation here, written in Python, begins with the world, and the world just contains entities in them. And entities can have positions. In my case, I actually only have one, which is the rover. And entities can also move. But so you can see that anytime my entity gets saved out, it's actually put into Redis. So I have a Redis stream in this case. So a stream is just a sequence of records. You can have any number of them. They're all attached with a timestamp kind of ID to them. And so any number of other Python scripts, for instance, could read from that stream and make determinations about whatever it saw, or it can just replay something that it saw before. So for this instance, I'm using the streams to where when the simulation ends and starts back up again, it actually can just start off where it left off by reading kind of the positions of the entities that were saved out, get loaded back in. This is probably a little bit more advanced than is actually needed for a hello world, but I got kind of carried away I was like, well, I gotta have persistence. I don't probably really need to have persistence at this level of it. The more interesting part of the simulation is the rover itself. The motor doesn't do anything too interesting except for just save whatever the power level that I have set on this rover this motor is going to be. My rover itself has 2 motors with names, and then the interesting part was the extremely rudimentary and unsophisticated method by which I applied trigonometry to try to put 2 motors together and determine what sort of impact that was going to have on the speed and direction that my rover was going to have in the world. I got something that kind of works to where if you can go forward, you can go back, and you can spin right and left, which is basically what my existing rover does. And it kind of operates on a similar scale. So the speed that the motor goes is like set by these constants up here, this velocity, and this is in meters per second. And so if I'm like full out on my little tiny motor, that's about how fast it's running. Okay, so how do I interact with that? As I mentioned, I wanted to not couple things too closely with like the command language that I was using, because I feel like that's something that could be iterated on more fully. So the simulation itself really only cares about the motor speeds that have been set. That's all it cares about. So what I've done in this case is I say my simulation is actually entirely a consumer of Redis streams that correspond to the motors. And I think this is actually pretty close to how you think about the architecture of something using ROS, in that you're going to have lots of different streams with different types of data on them. And the way you would design your entire ecosystem is how you link those programs together on streams. So a stream is going to like consume data, and then it's going to put something out the other side. This one is consuming 2 streams, motor A, motor B, and whatever the value is that I get off those streams is the power that should be applied to the motor. And so you can that's what's happening in here, is that I'm just consuming events, and when I see, oh, if there's a motor A event, it says set the power to this value, I set the power to this value. And then the simulation itself really operates on this tick loop. So every whatever the time step interval, so 100 milliseconds, I think is what that is. Every 100 milliseconds, we update our simulation by saying, well, if the power on the left wheel and the power on the right wheel were this much, then the rover should have moved forward this much. And then my command language is completely independent of the simulation, but it is also sort of the entry point where we write things into a Redis stream to cause something to happen. I've written this block of code so many times, it just about comes out, but it's just like, here's how you interrupt, or here's how you interact with a rover by telling it to go forward or backwards, or turn, or right spin, left spin. It's just setting the motor this value, setting this motor this value. And in this case, setting the motor means you add a event to the appropriate motors stream. And then this actually plugs in directly to where the Yak API left off, which is to say, when you have a set of commands that you want to send to it, you interact with the API, it starts this Python script, accepts all those commands over its sort of standard input, and then exits, and that's it. And the API server will just tell you what the output of those commands were, and doesn't really care beyond that. So I'm going to try to demo that. Does any of that our pieces interact? Does any of that make any sense yet? Or are there any way I could help make it
the
more
demo.
Okay, demo. Okay, so the what I've got running is what I said when I said show this Docker Compose file. The other thing that's running is RoverSim, and so that is just a Dockerized version of the Rover. Actually, this entire repository, I guess, RoverSim. This entire thing loaded up, and there's only one dependency is that it's got Python in it, and then I installed Redis, which is the Redis client for Python to be able to interact with it. So super simple. This is, I believe, running. So if I do RoverSim, what am I going to see? So this simulation is currently running. You can see like the timestamp that, well, I think this is replaying all the logs. But what the simulation is doing is showing where it thinks the rover is and what direction it's facing. You can imagine the rover itself has no idea where it is or which direction it's facing because it has no compass or anything else yet. And this is just catting all of the logs for however many days this thing has been running. So I don't know how long that's going to take to get to the end. I wanted it to just be able to hang out at the end so we could see it working. You know what? Maybe I'm just going to kill this thing. Stop. Okay, so hopefully that is going to now be waiting for these events to show up. Okay, so over here, this is on my laptop. And I created this shell script here that uses curl to interact with the Yak API server running on Yak Prime. And all of this gobbledygook is just to say, we're going to post the contents of what I type in after this command runs, and we're going to post that to this endpoint, and then it's outputs the result. So if I run CI, it just kind of sits here at this command prompt. I said, I want to go forward 100, and I hit, this is nice and esoteric, Control D to end the input, and then it runs it. So processing done. So apparently it ran this command. The problem is this is doing something weird with how it outputs my logs. And also 100 is not very far, so sometimes you can't see how it impacts the position. But there we go. You can see it spin there. So that's my hello world. The other thing you can see is what this looks like kind of on the Redis side. And so I wrote a little simple Python script that just says, that just makes it easier to see, watch a stream essentially to see like, hey, what are the contents that are coming through here? So in this case, I'm going to stream just motor A. And so if I do CI, go forward 1000, because it's nicer to be slow. You can see it spun up motor A to 0.8. And then it's going to take a while. And then it stopped it back to 0. And Yeah, and I can also, I think that also can do more.
So Redis is more like a log of the comments.
I'm using it kind of like a log. That's the stream stuff does, and so really it's very comparable to what I later understood about ROS as a middleware is fundamentally AMQP or something, which is a message queue protocol that's a standard that can be used in a more like industrial setting, I guess, is the idea. And what that means is that it provides a server with certain channels and a data format that you're going to use to interact with them. And so you put stuff into a channel and some number of consumers are going to be able to pull stuff out. AMQ, can't remember if that's AMQP.
So
yeah, this advanced message queuing protocol. So Redis started out being very, very simple with these very simple data structures, but then I think they realized like, oh, you can actually build on top of these to build things like queues, kind of replacing a lot of more complicated components. And there's plenty of reasons or plenty of context where Redis is no longer becomes appropriate, but it sure is easy to use and very fast when used in that in the context that it does work well in.
What is it generally used for?
Probably the most popular thing it's used for is it is the default backend for any Ruby on Rails project for running background jobs. If you know what a background job, so background job and like, so you had like a web service, and you wanted to do something that took place outside of where the like the web request itself. So if you say, what's my website is blog, I have a blog, and when I post a new blog entry, I want to regenerate an RSS page or something, or send an email. That's the more classic thing. Post a blog entry, sends an email. What that does in the Rails world, that would say you store the new blog post in the database. That all happens while the user is waiting, but then you in queue a background job. And so you put that into Redis, and then some other process, some other Ruby process that's running somewhere else pulls that off and sends the email. And then the user did not have to wait for that email to be sent. That's a very common pattern in applications like that. And Redis is used for that. I can say I've seen Redis used in that way to very large scale, but it does break down eventually because it runs on a single core on a single machine and doesn't necessarily it doesn't easily become web scale, and that scale horizontally forever. And that's what a lot of these other kind of more sophisticated message queue type architectures are really interested about doing. They really want to make sure that you can have multiple instances of the message queue operating on multiple machines. So if one fails, the whole thing doesn't go down, and you can scale it out to as many consumers as you need and as many cores, and it's infinitely scalable. Infinitely. Redis, on the other hand, said, well, look, you can do a lot with one core, and it sure is pretty simple if you do it that way. And for a rover, it really works well, because if the rover doesn't work, then it doesn't matter anyway.
But the thing also is that Redis is small and very fast, and it was used a lot with the Rails. It was carried a lot by the Rails ecosystem, but there is also a frequent use outside the Rails ecosystem, which is just to use it as a cache.
Yeah.
Okay. Very small and fast, and so it can be used with. There is almost any language can interface with it, okay? And so it's very useful as a cache. Okay? And it's interesting cache technology because it's a key value store. Okay, so it's a full database, and there are a lot of primitives. I think there are primitives, right? Like keys can vanish after some time, basically. Okay? Stuff like that. Okay, so it's really flexible cache, and it was also very popular in the past because back when it was completely open source. Okay? Now there is a company behind it, but my knowledge is that there was some work also on clusters of Redis, okay, to make it web scale.
Yeah, of
There
course.
is a running joke about web scale, but anyway. One question is that on the flow, okay, so it's like you have the rover running, okay. The Redis component is part of the rover, or it's just some. Okay, yes, and so it means that it's like it acts like a buffer that we send keys, we send comments to the rover listening component.
Yeah.
That listening component put that in Redis, and another component in the rover will read comments from the buffer and execute them. Is that something like that?
Yes, that's exactly right. And so that's in
Okay.
contrast to what I had originally intended was like, look, this is a Linux system. It's not that hard to pipe commands from one thing into another one. And so you could put it in a file and it could just read those things off of a disk or whatever. But what I found was that when you're dealing with multiple languages, especially knowing exactly what that pattern is for that language and how to do that in a way, especially if you're dealing with like Docker and having to like not exactly being on the same system, but sort of the same system, it gets a little bit confusing to like need to share the file system and know where to put things and how to access them, how to know when something new showed up on the file. That kind of stuff got just a little bit like, it's all doable, but it's like, oh, this is kind of a pain. I don't want to spend my time doing this. And whereas Redis is like, well, if you've got this one data server that's available, and as long as you can make that data server available to all the processes that need to encounter it, and that's pretty simple, then that's all you need. And then I'll stop. I like some of these data structures might actually be super helpful. For example, I don't think I mentioned this, but the first thing that I did was so I said that like there's a timestamp that goes on here. It actually starts off the timestamp that it left off at. So there's one key that's just roversim ts that is the last timestamp where it left off. And so if you were in the simulation, if the rover was moving forward and you exited the simulation before it stopped, you could start it back up again and it would actually continue on moving as if it were moving, and then like stop as if no time had passed whatsoever, because it knew what time it exited and it knows what time when it starts at. So it's like, oh, hey, I'm just using a key value here, but I can use like streams for other things, and like I don't know, any of these data structures might prove useful.
Thank you. And so it's there's just one technical question here that inside the rover, so the commands come to Redis, and Redis streams them inside the rover. And right now there is another piece of software that reads the commands. Okay, so, but does your software now support or already supports many software components listening to Redis? Okay, where you know in AMQP you have a command, you can fan out a command, meaning that there is one command that comes. So for example, forward 100.
Yep.
And right now maybe it's only one motor, so you have only one consumer. Okay? But maybe, for example, the spider boat, we have many motors to move the legs, so that forward 100 translates into actually many internal commands. And so there will be many listeners. There will be all the leg motors listening to one command, which is forward 100. How does it work for now? Is that could we use it directly on the spider boat, or there is some limitation here at this point?
Yeah, so that's important question of really what data structures that you want to use. And Redis has a way of supporting, I think, a lot of those messaging patterns. And that's 100% like why a lot of those messaging products like AMQP and I call them Rabbit or something. These other like queuing products have like these different messaging topologies or whatever you want to call them, or can get very sophisticated and very complicated to deal with. Redis does handle that through essentially kind of different, a few different mechanisms. the way I'm using this with streams, so streams is like a primitive that it has. And by default, by just out of the box, the most simple way to use streams is that any number of consumers can read off a stream. The consumer just has to decide where it wants to start in the stream and how many things it wants to read, and it can always go back and read more. And there's no state stored, for instance, in Redis to know who has read what. Like it doesn't care. It's just like, here's a sequence of values, and you can read whichever ones you want. You can read the end, you can read the beginning, you can read somewhere in the middle. Totally up to the consumer to choose whatever they want to do. So that's why in this example, I have this like stream command is watching the very same stream that the simulation is up here. And so when we saw it outputted, power 0.8, the simulation saw that at the exact same time and started applying that to the simulation. There are, it's actually much more complicated to limit how many consumers see a particular event. I think there are ways to do that, but I didn't care at this point, so I didn't try to implement that. It would be easier probably to do it one-to-one if you really wanted to make sure that you're putting something into a data structure like a list and saying there's another thing that's going to pull a thing off the list. That was that L push and L pop thing that I was doing.
Okay, but it's possible anyway. So it's
the way
depending on the use. Yes.
Yeah, the way I did it with streams mean that by default any number of things can read from it, but there's also the other implication of that is that there's no such thing as a response, really, right? Like we put in that we want the motor to be at 0.8, but there's no like way for you to say, aha, I did it, success, and like pipe that back to it. So that's, I think, kind of the tricky part about dealing with streams of data as opposed to request responses.
Yes. Thank you. Do you know in the ROS ecosystem, maybe ROS 1 and ROS 2 are different, but what kind of technology they are using? Because basically the ROS system is a set of nodes, and there is a kind of a pub subsystem behind it. For these nodes to.
I'm glad you asked that because I wanted to. What I figured out so far was entirely ChatGPT based. I asked what did I ask though? Somehow it told me what the messaging system was.
Isn't it using something called DDS or something?
Yeah. What? Yeah.
Maybe something like that. Yes.
How does ROS use Redis?
Does not.
No, it does not. How does ROS use?
But
do message passing.
you know that, but if yes,
Can I trick it into thinking it? Yeah. Well, it's at least a lightweight messaging library. ROS CPP. Oh, that can. Oh, these are the libraries that you would use.
These are just libraries, yes.
Okay.
I don't know. I think Anurag is right. Okay.
What is the messaging protocol or publish subscribe in ROS? Can you type that?
So it's talking about ROS 1, which is also very different from ROS 2 at the core.
Oh, yeah.
So ROS 2 uses object management groups. It's OMG. So it uses OMG DDS, which is a distributed distribution service, I think. And we're going to talk about DDS, or is it going to be wrong?
It might just
remember ChatGPT is very convincing.
It sure is.
It's very sure of itself, and it's like British nobility. Seldom wrong, but never in doubt.
Yes.
I don't know about seldom.
No, that's what they used to say. Fine, seldom like, but never in doubt, you know.
But yeah, the message passing service in ROS 2 is DDS,
Yeah.
which is very different from the service in ROS 1.
And that, I'm guessing that must be that was a critical one of the underlying reasons why ROS 2 was more what people wanted ROS 2 was because it could use this system that is other things can interact with.
Red, how do I play with your simulation? When I say play, I don't mean make a copy on my computer. I mean, I want to treat it as a real robot,
Mhm.
and I want to update the modules in the rover simulation
Yeah,
and test them by talking using this channel from my computer.
great question. So, there's a couple things I wanted to mention on that. One is that when you're playing with it, you don't get a lot of feedback, so it's not very fun to play with yet. And so the next thing I was working on was actually how do I get the data that you can kind of see here in a way that would be
Graphical.
at least graphical would be great, at least like viewable from something. I mean, and this like works actually very well, but like the logs out of this thing are kind of like kind of awkward to get at. So there's that aspect of like, well, you can like anyone who joins the Tailscale tailnet on the GitHub project can run this command and interact with it. All you get out of it is like this data. You have to be like logged into the machine and look at the logs to see what the simulation
but
actually thinks.
am I seeing the same instance that everybody else is seeing?
Yes. So there's one Yak prime, and that would be the one that this CI thing is interacting with. Now the change in the software, that is also an interesting aspect to this. So like I said, there's this, they're running in Docker right now. Cat dog. And the simulation itself is this image right here, which is coming from this repository. When I make a change to it, it automatically builds a new container through this thing. It built a Docker image. So what I was doing is just doing like Docker compose pull, and it will look and try to download. Oh, now I'm updating Redis, but it'll download. This was already up to date because I haven't changed it since, but it'll automatically update that image. And then like run the new version of it. That's not super useful for like, I mean, it's not super fast in your like turnaround time. So it also like runs locally very easily, which is where I did most of my development, but it's pretty easy to update on the rover itself. The Yak API server is actually a little bit more sophisticated in that. Maybe I don't know if I demoed this last time, but I had it set up to where I'm similar to where this one will build a Docker image. The Yak API will actually not only build stuff, but it will deploy it in just a few seconds, because and then this was kind of an experiment to see if it'll work, but I was able to figure out how to configure GitHub Actions to these like the CI jobs to install Tailscale, configure Tailscale to authorize this particular thing to work. And then it can actually communicate directly with the rover through this job. And it even tests it, like when it runs it interacts with the rover. Here, so every time it deploys it, like it communicates to the rover to ask it if it's okay.
That when you say rover, you're actually conflating the rover and the simulation the rover's running in, right? You don't have separate objects, so to speak.
I guess the rover is running its simulation on board. in a way, or well, I don't know. I
But
don't know.
I mean,
How do you talk about
the
that?
rover can't walk and bang into a tree.
Correct. This particular rover, Yak Prime, exists only as a VM running in a closet in my house.
No, that's
Yeah.
fine. I'm saying in the imaginary world this rover lives in,
Yeah.
there are no trees.
Oh,
Unless
right.
the rover itself believes there's a tree. So I guess in parallel to me wanting to be able to access and you wanting to be able to show the data, I think it's important for us to split apart the rover and the world simulation.
Yes. And so the split in this, so I think that gets to a very important part that I was trying to figure out where the right lines should be drawn. Where do you draw the lines between those things? And I think it is, in this example, the line is what power level do you set a motor at? So it's really about communicating with a device on board the rover and telling it to do a certain thing. And that's where the line was drawn. So there's two things in the rover sim that probably, there's one thing in the rover sim that shouldn't be there. And that is this CI script interprets commands and sends them as, sends them into Redis here. This should not be part of the sim. This is part of the rover. It's really like how the rover interprets commands, and that's sort of independent from simulation. But this other part, main, which is running the world, that's pure simulation, and the rover doesn't even need to know it exists. All it is reading from Redis streams about what someone asked motors or actuators to do. And it should also work the other way, where sensors are coming out of this.
So I take back what I said.
Oh, okay.
I need it to be split into three. One is the world,
Okay.
one is the rover, and one is the brain of the rover. So I need there to be a world that somebody can update and maybe even move me into Gazebo. Different rovers have different reactions to commands. You know, physical reactions like flapping arms, turning wheels, and so on. But the brain of the rover, that is like a separate entity. I give it a command and it tries to do something. Now, maybe I'm wrong and you shouldn't separate the brain of the rover from the mechanical, electrical response of the rover to what it's trying to do. But it seems to me I'd like them to be separate elements so that different people can play around with them. I can imagine, I don't know, Venkatesh uploading his mechanical model, and that would somehow get integrated into the simulation of the mechanics of the rover. And I would, let's say, upload my garden, and that would somehow get integrated into the simulation of the world.
Right.
And when I say integrated, what I really mean is that we find a way to glue it to existing simulation programs, not that we would actually, you know, write that software. So my question to you is, can you think of the correct way from a software perspective of taking your Docker and somehow dividing it into three parts which talk to each other, not to us?
I think that each one of those, any number of components, can run independently. The contract is it's going to read things from Redis and it's going to output things to Redis.
Okay.
Except for this one piece, which is, I guess, the user interface. And so you've got to have something that acts as user interface. In this case, it's this simple text line-based language that says go forward, turn right, do whatever.
Oh, so wait. The user interface is running on your computer. The part of the rover that knows how to respond to these commands, that's part of the rover.
It is running on the rover, yeah.
Unless you mean that there's another module which translates these commands into Rover language. And then
Actually,
that-
no, I think the way it's laid out now, I would say that this is Rover language. And we could have any number of Rover languages that we wanted. But this is the closest thing I think to the brain in what you're talking about is this right here, which is both the interface and it's the thing that's going to decide how to respond to anything. In this particular case, the only thing we're responding to is operator instructions, but you could probably extend that to do whatever you wanted. But you could also say, well, my brain is actually 3 different Python scripts all running at the same time. And some of them are responding to sensor data that is being emitted from the simulation. And some of it's responding to internal timers. Some of it's responding to, whatever. And you could have multiple brains that are all trying to control the motor at the same time too. Because they can all write to the same Redis stream that says set motor A to half power. That make sense? Maybe.
I think so.
Yeah, and as I said, this CI thing probably shouldn't exist within the same even repository or whatever. Like these could all run. This could be completely independent of. Oh,
So-
actually,
so how do
even
we
this
set
import
it
shouldn't
up?
be there.
How do
That
we
was
set
left
it up so that we can collaborate on it?
I mean, I think that right now, anyone who connects to the, or no, I have to do a little bit of work. I think, did anyone else figure out if they can SSH into the VM?
I'm pretty sure I was able to eventually, but I feel like I got booted. I think I got booted off the tailnet. But I feel like, because I know we were trying to get into our boxes for a while and I thought it eventually worked.
Yeah, I thought I figured out how to do that. But without wanting to set up like your own sort of environment to write a brain, for instance, the easiest thing would be literally to have access to like SSH in, and as long as you can connect to the Redis server that's running on the VM, then you can kind of have it do whatever you want. You could write your own brain that told motor A and motor B to do stuff. And I say that just because like I think I can set this up to be exactly like the Yak API thing is, where you could write code in this repository, and then when you merge it in, it automatically deploys and runs on the rover. It's just a little bit slow to do that. If that makes sense. This also runs perfectly fine locally. So for experimenting, as long as you run a Redis instance, you can run this locally on your computer, and then you've got a rover simulation that and the brain, because and the brain is written in there. I think the next obvious thing for the simulation is to have some sort of sensor data, some sort of response that you get. Like my first rover had the impact sensor if you hit a wall. So I can imagine like putting a wall around the simulation playfield and doing some sort of simplistic object detection that triggers the impact sensor if you hit it. Or maybe reinventing it all from first principles is way too time consuming, and it's better to wire it up to a real simulator. I don't know. It's kind of nice when it's really simple though.
That's step 2.
Mm-hmm.
In other words, once we have these different parts, we try to take each part and connect it to a real simulator.
Yeah, I feel like if the architecture is right, then it should be not impossible to replace elements with something else. Like even the simulations that we looked at had these ROS connector components, right? So you could imagine a Redis rover
That is the ROS.
connector. Yeah, something that it's essentially the same fundamental architecture, which says you've got streams of sensor data, you got streams of commands from some brain, and the simulation has to run those.
You know, your work today reminds me something very old, but conceptually that can be interesting. It was in the 80s. There was someone, and I forgot his name. I read many of his papers, and for some reason I can't remember his name. But the programming language was called Linda. Okay, and Linda was it can still work, but it's called a blackboard-based language, and so it's for distributed systems. And so it's what is pretty cool is that basically you have a huge shared memory, so called the blackboard, and processes that interact. And so here the equivalent will be Redis for the blackboard. Okay? So we have many processes writing to the blackboards and many reading from the blackboard. And they have a very limited set of primitives. Okay, so you can write, and if you write on something that exists, that will overwrite it, and you can read or read and consume, if I remember well. Okay. There is one more extra thing that every action is based on a tuple. Okay, so a tuple is a funny name for a list, basically. Huh? And so what is pretty cool is that you know, you define each command is you define a tuple that either you write or you read. And what is cool is that it can be incomplete. The tuple can be incomplete. You can put holes in it, so it will automatically match to all tuples that match your pattern, basically. Okay. So, for example, you see in the demo we have in Redis we have a kind of log stream of forward, motor on, motor off, and so on. Okay. And so we could have a tuple, okay, that says forward and without arguments. And so it would find all commands that are forward and we've done forward 100, forward 200, maybe a timestamp, stuff like that. Okay? And so what was pretty cool with Linda back then, because in the 80s, well, I think a lot of us were not at the university yet. Okay? Yes. So that was pretty cool because so first it was a formal model too. Okay, so there were some proofs that it was correct and so on. And there were a lot of guarantees as a distributed system. And thanks to your work and your demo today, I realized, or I completely forgot that what we're talking about here, what we're talking about quite often, and what you can see with ROS 2 and maybe ROS 1.2 with their structure in terms of node and the communication fabric and a protocol behind it. Basically, all these patterns, they are more or less instantiation of modern instantiations of this Linda pattern. So your last comment about architecture for me is pretty right. Okay, that if we get the architecture right, there are a lot of things we can just swap. Okay, we can swap. We have this blackboard concept, and it's implemented here in Redis, and in ROS 2 is maybe some DDS kind of adapter. Okay, anyway, so it's a bit more of a historical note, and also to highlight the point that with a good architecture, a lot of things we can swap easily. Anyone has heard about the Linda programming language? I need to search because I don't remember the name of the author.
When you started talking about Blackboard as a construct, that sounded super familiar, but maybe you talked about it before. That's my best guess.
Perhaps, yes.
Where? That's not. It's yeah, just real big memory.
But so Linda is what's called a coordination language. Okay, I didn't even remember that. Oh yes. David Gedatner. Okay. It was 1986. Wow. I was almost 10 then. Yeah. But what is a bit also scary that, you know, is the feeling that we are reinventing the wheel over and over. Okay, we talk a lot about making good wheels for the rover project, okay, but it can be a lot of wheels actually.
Yeah, it's kind of just implementation details. The implementation details change, but the idea is kind of all the same.
I'm pretty sure that it's first it's good to reinvent wheels, okay, and also because I'm unable to say now what were the shortcomings of Linda back then, okay, because surely they were, okay. We've made progress on many fronts, okay, and you see when we look at DDS is from the OMG as Joshua mentioned, okay. The OMG, you know, that was a big group like more than 20 years ago. Okay, I mean, these people did something called Corba, and people who hear this word, you know, they have very bad memories. Okay, I had to work on Corba. I mean, no, because the thing that it's supposed to, you know, to solve high-level problems. You know, it's distributed object communication. Okay, it looks like easy and so on. With Corba, it's hell. Okay, it's really hell because you know basically the abstraction level is just not right. Okay, and so it was a fantastic project, but the thing that and it provided a lot of learning that allows actually modern distributed systems to be better. But the era of Corba for me is like no, never go back. Okay, and
Dark
and
memories.
so when I see now DDS from I had a quick look now about the architecture and so on. It's like, ooh, ROS2 wanted that. Okay. Anyway, conceptually, it's the same concept, but in terms of implementation, I'm sure we have a lot of things done since then. And now with you know, we've talked about protocols. I think Venkatesh talked about protocols, a few interaction protocols. That's exactly the kind of thing where there is potentially a lot of things to innovate on. Okay. Although it also matches the Linda pattern to some extent, there is more to it. Yeah. So I'm pretty convinced that revisiting, re-implementing with modern tech, with modern ideas and so on is really, really valuable. Okay? For me, this comment was more a historical comment, okay? And also to see that there are concepts, only concepts that we are not really what can be interesting that back then, when maybe it was simpler and there were people spending a lot of time on formal verification and stuff like that, it can give ideas, it can guide on what we're doing also, and to avoid some conceptual issues that we lose because we are looking at it from a different angle, basically. Okay.